All right, ladies and gentlemen.
Hey, YouTube.
Hey, guys. So we are starting this out YouTube Live again today. As I said, my voice is worse than yesterday, which is worse than the day before. So I doubt I'm making it all the way to 7th hour today. So they can watch this. And plus, this is streaming live, which means it's instantly on my YouTube channel. So I upload it or put the link on the website right after class is done. So it's there for you to watch later if you need extra practice and you need to go back and look at things. The agenda for today, we're going to take a look at the pH of weak acids worksheet from last night. Some of it I gather was tricky, but I think once you see it, you'll have that, oh, hey, that makes sense. Because some of it involved problem solving that we didn't touch on necessarily in class, but I trust that you can figure it out eventually. And then from there, we will talk about strength of bases. Yesterday we did acids, today we'll do bases, and then talk about KB and weak bases. And we'll also talk about neutralization, which is really super brief. So on the first problem you had, it asked you to find the pH of a 0.065 molar solution of formic acid. I just went ahead and called this HX just to save us some space. It says the acid dissociation constant, which is like our weak acid equilibrium constant. For formic acid is 1.8 times 10 to the minus 4. So what I went ahead and did is I set up my equilibrium equation, indicated that my initial concentration of the HX is 0.065 molar, and we have no products to begin with. Again, there's nothing we put for water because water is pure and it's not part of our equilibrium expression. We undergo a change during equilibrium or to achieve equilibrium, and so we call that, hey, we're going to subtract some amount X from the reactant side, and then as that acid dissociates, we gain X amount of hydronium and our anion on the right side. So at equilibrium, the concentration for HX or formic acid is 0.065 minus X, and then we have X for hydronium and X minus. So from there, we set up our equilibrium expression, which is our products over our reactant. There's no coefficients to speak of, so there's no exponents here. And then I plug in our variables accordingly. Hydronium and X minus are both X, so we have X squared over HX, which is 0.065 minus X, and that's equal to the Ka that was provided. Now we're assuming that the value of X is going to be much, much smaller than the concentration of HX that we start with, so we can effectively cross it out, and that simplifies our math. So we multiply both sides by 0.065, which gets us 1.17 times 10 to the minus 5 equal to X squared. To find X, we take the square root of both sides, which gets us an X of 0.0034 molar. And if we look back at our equation in our ice table, we see that X really is our hydronium concentration, where we can substitute in for hydronium concentration. So if we remember that pH is the negative log of hydronium, we can take our X, plug it in here for hydronium, and we get a pH of 2.47. I'm coughing for obvious reasons, but yesterday, 7th hour, laughed a lot during the video because a lot of you were coughing and sneezing consistently throughout the video.
Okay, so when I put the calculator
Close enough.
okay.
What I did, did you put in negative log of 0.0034? So what I did is I just kept the value in my calculator. I wrote it as 0.0034 here just to show the work, but then I just did negative log of answer in the calculator to get this. Okay. Yep. So like I just said to Jenny, here I just rounded for the sake of putting it on paper, but when I did negative log of that value, I just did negative log of answer from my calculator to get to 2.47. So if you had 2.45, 2.47. That's good. All right, let's take a look at number 2. Number 2 says find the pH of a 0.325 molar acetic acid solution. Ka is 1.8 times 10 to the minus 5. Acetic acid, I did HA. Again, it doesn't matter what you put there. Checks, HC, HQ, HA. But I did HA because acetic acid made sense. So my initial concentration here, 0.325 for HA, nothing for the products. Change is minus X on the left, plus X on the right. So at equilibrium, those are respective concentrations. Set up our equilibrium expression, which I went ahead and I set it up here in 1. Assuming it's the same setup, I just plugged it in down here. So that's our Ka. Hydronium Na minus, our X are combined to be X squared. We're assuming X is much smaller than the 0.325, so we cross it out. Multiply both sides by 0.325, and that gets us 5.85 times 10 to the minus 6. That's equal to X squared, so we find the square root of both sides, and we get about 0.00242 molar, plus some other digits, because I just kind of rounded for this step to get X. And then I still had it in my calculator, so I did negative log of the answer in my calculator, which was hydronium, and I got 2.62 for the pH. Okay. How are we doing so far with these two?
Good.
Okay. So the practice that we did in class yesterday mirrored these two. Now, I'm guessing some of you got a little nervous when we got to 3. So for 3, yes, there's a lot of work here, but let me explain. They want to know a pH of a solution that has 0.0034 molar lactic acid with that Ka and 0.056 molar of propionic acid with that Ka. So the goal is, since we have 2 acids, we need to find the concentration of hydronium from both acids and then add them together to get the total hydronium concentration in the solution. Huh? Yeah.
I did that. I got it right. All of it.
So we need to set up 2 ice tables. The first ice table is for the lactic acid. I just called it HL for lactic. And so we set it up following the same setup as 1 and 2. We get an X of about 6.899 times 10 to the minus 4 molar. That's for the lactic acid. And then I did the similar setup for propionic acid on the right side here. And the X I got for that was 8.854 times 10 to the minus 4 molar. So we have our X being our hydronium concentrations. If I add them together to get a total hydronium, then our total hydronium concentration, if we add them, comes out to this value, which I just wrote the full calculator answer. And then pH is negative log of hydronium, so we plug that in, and we get 2.80 for the overall pH.
You added the X values.
Yes, because the X values represent hydronium. So if we know hydronium from one acid and concentration of hydronium for the other acid, since they're in the same solution, we just add the hydroniums together, and that gives us the total concentration. And then we find pH according to that concentration, and that's the overall pH for the entire thing.
Wait, so the X values, there was like on each side, but not like so long.
Right, so the X is just our X here is for hydronium. And then this X goes up here for that hydronium. So if we add them together, then we have the total hydronium. Okay? Shh. So I know that was tricky, but the idea is we find it for both, add it up, and then we get the total pH. Fair enough?
Yeah.
All right. For number 4, we're finding the pH again, given 0.00056 molar butyric acid. And in this case, they give us the pKa, pKa, we can find it just like pH. So if you didn't know this, you could look it up. pKa is the negative log of the Ka. So if we do the inverse log of the negative pKa, we get a Ka of 1.51 times 10 to the minus 5. And then we do our ice table just like we've done up in the other problems. Eventually we find an X that is 9.2. I just worked the full calculator answer out, times 10 to the minus 5. So pH is negative log of that concentration, and we get 4.04 for the pH. So the tricky part in this problem was finding out what Ka was. And you could have done this one of two ways if you're stuck. You could have looked up to see how do I calculate Ka from pKa, or you could Google Ka of butyric acid and you would get about that value.
We can't Google on the test then.
Yeah.
You can't. So now you know how to do it.
Should be able to.
Wait, actually, someone look up the answer.
pKa is equal to 10 to the negative pKa.
Wait, well, say it again.
I don't think so. This is an exercise in problem solving. Probably not. All right. So if you need to go back over this later, it'll be up on the video on the website after class. Okay, so let me check something. Okay, your homework, by the way, has two problems. One is a weak acid problem and one is a weak base. So you're going to get more practice. And it's going to be more in line with what we did in 1 and 2, but it's going to break it down in steps. Although your quiz is just like one of these, it's not in steps. You have to work through the whole thing. But you're capable. All right, go ahead and pull out your slides. We don't have other questions here.
Do we need our notebook again?
Yes.
Okay.
Huh?
Actually,
Yeah, there you go. Wait, so on the slide, she's the other test?
On the test,
On the
yes.
quiz?
On the quiz, no. We went through KA for yesterday.
So this stuff that we're going to do tonight?
No, but it's the KB is very similar to KA.
Just to go back to your acid,
Huh?
right?
Correct.
But Casey will not be on that, so what we're gonna do.
On the quiz tomorrow.
Okay, that's it. Okay. So it's just up through the
All right. All right, folks, let's take a look here. So strength of bases. It says similarly to weak acid or to our acids, strong bases fully ionize. So we'd see something like sodium hydroxide, which is a strong base, plus water. Will completely ionize. And because we're saying it's in water, these are both going to be aqueous. That's where the rest of the water comes in. So that single arrow completely ionizes, so it's 100% ionization. For weak bases, something like, I don't know, ammonia, if we add that to water, we're going to set up an equilibrium where we look at the Bronsted-Lowry case here, where we make our conjugate acid, and then we make our conjugate base. So the fact that we have an equilibrium here says that we have less than 100% ionization. It's incomplete. So similar to how we talked about, strong acids, we said with strong acids, you had more proton ions in solution, so it was stronger and more dangerous. Similar idea with strong bases. The more hydroxide ions you have in solution, the stronger it is and the more dangerous. And then in the case of the weak base, we have less hydroxide in solution because it's in equilibrium, so we don't have complete ionization. Okay. Some of our common strong base examples, we've got 3 of them. We have sodium hydroxide, potassium hydroxide, and calcium hydroxide. Anything else we come up with in any other hydroxide type base is going to be a weak base. I'm all out of tissues now.
Forever? I
Yep.
might have some in my locker. Kobe! Do you want more? I can give you some for tomorrow. I'm gonna bring in like a box or 2.
I can bring some from home. Yeah. We hit up Sam's Club for tissues. Okay. I mean, if you want to bring tissue boxes in, that's fine, but I don't do extra credit for tissues. In fact, the district has a statement about that, and it's heavily frowned upon.
Yeah, for
All right. So we just looked at strong bases. Now, in terms of weak bases, to measure the strength of bases, a KB expression tells the relative strength of the weak base that's set up in equilibrium. And just like acids, the bigger the KB value, the stronger the base will be. Okay. But even if we have a large KB value, realize that we're still going to be a weak base. Okay. And for the most part, I've never seen a KB that's greater than 1. Right? Because greater than 1 would suggest that products are favored, and if products are favored, you might think it goes more towards completion, which it doesn't. So weak bases, we should have less than 1 still, but if you're comparing values, the bigger the value, the stronger the base is. Okay, so let's look at an example here. So for weak base equilibria, equilibria is the plural of equilibrium. The problem is as follows. Calculate the pH of a 0.10 molar NH3 or ammonia solution. Kb of ammonia is 1.8 times 10 to the minus 5. All right, you guys have the problem written down for most of the way. So remember, one of our first steps is to write the chemical equation. So in this case, we have ammonia plus water. Sets up an equilibrium, and our conjugate acid is ammonium, and our conjugate base is hydroxide. You guys see the black pen, okay?
Yeah.
Okay.
Yeah.
So as we look at this, right off the bat, I'll skip that part. So let's go ahead and fill in the information that we know. We know NH3 initially is a 0.10 molar solution, and our products, we should have 0 of them because we haven't put it in water yet. And then after we put it in water, we undergo a change where we're subtracting some amount on the reactant side and we add that amount to the right, because the idea is that ammonia is reacting with water, and so there's some amount of ammonia we lose and we gain the same amount for each of the ions. Okay. So then at equilibrium, our concentrations are as follows: 0.10 minus X, X, and X. Okay, so let's set up our KB. So KB for this equation is the concentration of ammonium times the concentration of hydroxide divided by the concentration of ammonia. And if we plug in the values that we know that we have KB of 1.8 times 10 to the minus 5. That's equal to effectively X squared, because it's X times X, divided by 0.10 minus X. Okay. And a note here for the base: when our base concentration, here we go, is less than 1, X will change it minimally. Okay, and what that means is that we can effectively, again, cross out X in the denominator, because it's not going to have a huge impact on changing that concentration. So we're saying because this is 0.1, since it's less than 1, whatever amount of X that we change, it's not going to change that concentration very much. Okay, it's an insignificant change. So at this point, we want to solve for our variable of X, multiply both sides by 0.1, which would be 1.8 times 10 to the minus 6 equals X squared. What do we do next? Square root of both sides. And what does X come out to? Huh? Times 10 to the negative third. Okay. I can't hear it very good, apparently. I had it in mine in standard notation. You had it in scientific. It's the same idea. So 1.34 times 10 to the minus 3, or in standard notation. So we want to find the pH. Realize for a moment that this X value here is the hydroxide concentration. Okay, so this equals hydroxide. So what do you think the best thing to do is right now? I mean, I know we want to get to pH, but what's probably the most straightforward thing to do from here? Yeah, find the pOH. Okay, so pOH is negative log of hydroxide. So we're going to take this value here, plug it in for negative log. And when you do that, what do you come out with? What you got? Okay, so that's the pOH. We want to find the pH. What do we do next? Subtract from 14, right? So we remember pH plus pOH equals 14. Plug this into here. So pH will be 14 minus 2.87, which comes out to 11.13, which makes sense because we're dealing with a base, right? So the pH should be basic. Okay, fair enough. Okay, it's basically the same, It's the same thing as dealing with weak acids. It's the same mathematical concept. The only difference is if we want to find pH, we have to go the extra step and realize that what we're finding for X is our hydroxide, and then plug that in for pOH, and then go one step further to find pH. Okay.
On the product side, it's something other than 0.
Like here, those are 0 because I stands for initial. So our initial concentration, we have something for the base, and we put it in water, and at that very instantaneous moment, there's no product formed. So the product concentration is 0. And then as we undergo those reversible reactions, we get to a point of equilibrium where we've lost a little bit of our reactant, and we've gained that amount of products.
Yesterday we were finding the X of and 4 plus. Is that why we just
No, yesterday the X would have been hydronium.
we just sub that in for H?
No, ammonium is not the same as H+.
How come we could just, like yesterday, we just put negative log of X together?
We're dealing with a base, so if you just said, hey, this is X, and I do negative log, what you're getting is the pOH, not the pH. Okay. So it sounds like you want to take a shortcut here and say, oh, this is base, this is the conjugate acid.
What did the yesterday I just put in log?
Right. And that's because this part here was H+ or hydronium, and this was the conjugate base. But now instead of having an H+, we have a hydroxide, which is saying we're dealing with a base. Jackson?
So because this is it creates the OH ion, this reaction, is that how we know that the molarity of 0.00134 is the same as the OH concentration?
Yeah, because we solved for X, and we see from our equilibrium concentration that ammonium and hydroxide are both X. So what it's saying is that these are both the same concentration at equilibrium.
Okay. So in the case of if we were making like an H+ ion, like proton, it'd be that the molarity would be equal to the concentration of H+ hydrogen ions?
Yes, if this was for a weak acid equilibrium.
Okay.
Okay, but we're a weak base, so we have to think of it in the context of hydroxide. Any other questions?
Would there be a point where the base concentration is?
For the sake of our math, no. I mean, I'm sure you could, but I mean, if it was greater than 1, we wouldn't be able to cross x out, and what we'd have to do is solve it and get a quadratic formula or quadratic equation, and then use quadratic formula to solve, which is more work. You could put it in your calculator, and you get a positive and a negative, so obviously we choose the positive value. And if you did that, you're going to come out really close to what we got here anyway, which would go to show that the value of x is insignificant compared to what you started with, so the change is going to be minimal. Okay. Yeah, so if you do 0.1 minus 0.001, you get what, 0.998, which is still really close to 0.1.
Why do you still subtract x when the NH3 is the one getting the most?
Say it again.
Why do you still subtract x from the NH3 when the NH3 is the one that's receiving the group? You're not losing ions.
Well, we're producing different ions in solution, so it's the similar idea that we start with this concentration, equilibrium. We're losing a molecule of this and forming molecules of these, or ions of these. So just like we looked at yesterday, we could say, if we have, you had ammonia plus water yields ammonium and hydroxide. Initially, we might have 100 molecules of ammonia in none of the products. And so the idea is if I subtract 1 molecule of ammonia and I take that ammonia and it dissociates in water or ionizes in water, we're going to form one of each of those ions. So then the equilibrium is going to say, well, then we're down to 99 ammonias and we've gained 1 of each of those. Because I guess one thing I didn't mention yesterday, you have 100 of ammonia, and really we're saying if we have 1 water, for example, if I lose 1 ammonia, it reacts with 1 water. So, 100 plus 1 is 101, 99 plus 2 is 101. So we're still conserving the amount that we have there, but water's concentration is constant, so we don't include it in the expression. Okay, so there's one other thing I wanted to say here. If we have other bases, let's say you have like rubidium hydroxide, which is aqueous. We're assuming, of course, that it's in water that we ionize to make rubidium and hydroxide. Okay, so do you see in this case that we can't take the concentration of the rubidium cation and say that it's H+? Okay. I know before we saw with ammonium, like right here, that, oh, it's got an extra H+, whatever, but that's not necessarily the case. So what we can do when we have other bases is we can generalize. And we might generalize to say that we have ZOH or ROH or something like that, because our main focus, of course, is that we have the hydroxide part of that base, the exception being ammonia right there. Okay. Let's see here. I think I'm actually going to wait and we'll do neutralization quick because it's super quick. And I already put it in the title of the video. So if you turn to the next page in your slides, neutralization just says when an acid is added to a base, for example, hydrochloric acid plus sodium hydroxide, The products are salt and water. In this case, sodium chloride and water. This is a double replacement reaction where hydrogen is going to go hang out with hydroxide. So the H plus from the acid bonds with the hydroxide from the base to make water. And then the other two ions come together to make a salt. So sodium and chloride in this case come together to make the salt. And realize too, and we said this before, that salts are ionic compounds. Okay, so it doesn't matter what salt we're dealing with, it is an ionic compound. You guys see my highlighters?
Oh, yeah.
Blue, my pink highlighter.
I have 5.
There we go. All right, so on the assessment next week, or I guess the week after Thanksgiving for you, there will be a question that says, in a neutralization reaction between an acid and base, what are the two products? Salt and water. That question, if I'm not mistaken, is 6 points out of like 60 something.
All right.
I've made it a ridiculously high amount of points because it should be an easy amount of points for you to get.
What if we were really bad?
I've had people mess that one up. 10%. And I'm like,
Salt and water. Wait, what's the question?
Salt and water.
what are the products of a neutralization reaction? Salt and water. There we go. All right, so the homework we're going to get today covers weak acid and weak base, so it's more review of the equilibrium type of calculations. The first one is a weak acid. So in this case, it breaks it down for you stepwise. It is not broken down stepwise on the quiz, but I think it is on the test next week or the week after. And then you have a weak base one as well. In this case, they tell you what the pH is. So it's going to walk you through, and you're going to have to do some solving to do some things, okay?
You can